Hi, so my name's Abby and I'm going to be going over sections 1.6 through 1.9, which is measurements and calculations. All right, so let me share my screen and we will go over this PowerPoint. Okay. So the first part of this is accuracy versus precision. And these are important to think about when we are looking at values that we have found through an experiment. Accuracy is how close the value we find is to the true or the actual value. And in this class, we want it to be plus or minus 1% of the true value. So it needs to be pretty close to be accurate. And precision is if we repeated the experiment over and over, how similar would our results be? Are the values about the same spot? If they are, that means we are likely doing the experiment correctly, but if they aren't, then there's probably some error happening. And again, we want these plus or minus 1% of the true value. So here are some pictures to help us visualize what these things mean. So this one, if you shot these arrows at this target and they all ended up right here, you're precise because they're all around the same spot, but you're inaccurate because you're pretty far off from the target, the bullseye. Now this picture is precise and accurate because you have all of those arrows in the same spot, but they're also on the bullseye. This one is not precise because the values are all over the place. However, it is accurate because the average of these values would equal something pretty similar to right there in the middle because they're spread out evenly. But that's not very good either when we're running experiments. And this one is neither precise nor accurate. The arrows are all over and their average would be about here and not the bullseye. Okay, so here's some practice. So we have an object that's 100 grams and we need to decide if, so the real weight of the object is 100 grams and we've taken some measurements and we need to decide if they are precise, accurate, both, neither, and explain. Okay, so the first one, 112 grams, 118 grams, and 106 grams. They are not close together and they're not close to 100 grams. So that will be neither precise nor accurate. The second one, we have 99.7 grams, 100.1 grams, 100.2 grams. Now, all of these are really close together. They're all within 1%, which would be one gram of each other. And they are accurate, so they're precise because they're close, and they're accurate because they're all within 1 gram of 100 grams, which is our actual value. So that's the kind of results we like. Now C, we have 110 grams, 111 grams, and 110.5 grams. These are all really close together, so they're precise, but they are not within 1 gram of 100, so they are not accurate. And then this one is a little interesting. It is accurate because 105 grams, 92 grams, and 102 grams, their average is about 100 grams, but they're not precise because they aren't close together. They aren't within 1% of each other. So there we can see the answers. Okay, so whenever we have measured numbers, we always need units. It's easy to do the math and forget to write down the units, and the units are very important. And sometimes when you're doing problems, one value will be in kilojoules and one will be in joules, and if you don't write down the units, it's easy to miss that and get the question wrong. So write down your units and keep track of them as you're doing the question, and it will help. Okay. In chemistry, we use the SI units. for our standard units. We'll use other ones too, but these are standard. So for mass, the SI unit is a kilogram and the abbreviation is kg. For length, it's a meter and the abbreviation is M. Temperature, it's Kelvin. We'll talk about what Kelvin is a little bit later. For time, it's second. The abbreviation is an S. Electrical current is an ampere, which is just A. And quantity of a substance is a mole. With SI units, the prefixes are important. It's a base 10 system, so if you multiply it by 10 or 100, you can convert one unit from another. So for the test, we have been told to memorize through, let me go back. So deca through giga over here, getting bigger, and then deci through pico over here, getting smaller. So a meter, or the base unit, we'll use a meter for example, would be an M. And if you wanted a decameter, you would times it by 10. If you wanted a hexameter, you times it by 100. And so you can just move the decimal place over to the right if you are trying to get a value that's bigger, or if you're trying to get a value that's smaller over here, you move it to the left, the number of places. So 10 to the -3. So to get a milliliter, you'd move it over 3 spots to the left. And these are really helpful when we're doing dimensional analysis as well. Okay, here's temperature. So we're all familiar with Celsius and Fahrenheit, but in chemistry we use Kelvin. And a lot of the calculations we do will be using Kelvin. Kelvin is on the same scale as Celsius. So to find Kelvin from Celsius, all you have to do is add 273.15 to your degree Celsius. And to convert Celsius to Fahrenheit and vice versa, you have 5/9 times degrees Fahrenheit minus 32 equals degrees Celsius. So here we have an example question to practice these conversions. It says comfortable temperature is about 72 degrees Fahrenheit. Body temperature is about 98 degrees Fahrenheit. Convert these temperatures to degrees Celsius and Kelvin. So I'm going to stop my share so you can see on the white screen, the whiteboard that I have, how to do this. Okay, sorry, technical difficulties. All right, so we have 72 degrees Fahrenheit. And we want to convert this to Celsius and Kelvin. So to convert it to Celsius, we need to subtract 32 and then times it by 5/9, and that will equal our degrees Celsius. So 72 minus 32 times 5/9 equals 22.2 degrees Celsius. And to convert this to Kelvin, we're just going to do 22.2 degrees Celsius plus 2 73.15K, and that will equal 295.37K. Now this is not correct SigFigs, but we will talk about SigFigs a little bit later. Okay, and you would do the same thing with 98 degrees Fahrenheit. You would just plug it in here for the 72 and keep going with the calculations. Okay. All right, so let's keep going here. So SigFigs are important to help us have the most accurate measurements that we have. When we measure something, we always estimate one digit past what we can measure exactly. So here you can see it on this ruler. Right here we have 1 inch, 2 inches, and the line goes to right here. And we know it's at least 2 inches, but we don't know exactly what it is, so we estimate. We estimate that it's about 2.5. Now, this ruler is a bit more accurate. It has more smaller measurements. It goes to tenths of an inch or tenths of a centimeter, whichever it is. And so we know it's past 2, and we can see that it's 0.1, 0.2, 0.3, 0.4, 0.5. And you know, it's somewhere between 0.5 and 0.6. So we estimate it's 0.55, 2.55. This last digit that we estimate, we won't know if it's exactly right. So there will be some small error there. Now, these are the rules for SigFigs. Non-zeros are always significant. So any number that isn't a 0 will always be significant. The second rule, zeros between non-zeros are significant. So if you have, for an example, 105, the 0 between the 1 and the 5 will be significant. Number 3, zeros at the end of significant digits following a decimal point are significant. The reason this is because if you have a measurement that before you do the calculation, it has decimals, and after, for whatever reason, there's zeros there, you want to keep those zeros there to show that you know that position, that decimal point exactly. And number 4 is placekeeper zeros are not significant. So like if you have 0.001, the 0.00, those zeros are not significant. So these are zeros preceding significant digits and then zeros following significant digits without a decimal point. All right. Now this rule, dot right, not left, is a way that I learned SigFigs, and it helps me to figure out how many there are in a number. So what it means is if there's a dot or a decimal, and you start on the right counting the numbers that are significant. So for this one, dot, so you'll start right, 1, 2, 3, and then there's zeros. So those ones aren't. So there's 3 significant digits. And if there's not a dot, for example, on this one, then you start counting at the left. There's 1, 2, and then the rest are zeros. So there's 2 significant digits. So let's just go through these and count how many SigFigs there are in each one. This one is all non-zeros, so they're all significant, and that would be 6. This one is 3, like we went over. This one is almost like this one, but because these zero dot right, we start at the right, and we count these zeros. 1, 2, 3, 4, 5. 5 significant digits. This one, there's also a dot, so we'll start at the right, then we count from here, 1, 2, 3, 4, 5, 5 significant digits. If this decimal wasn't here, like it is in this one, like it isn't in this one, we do not count these zeros as significant. They're only significant because of the decimal. And then with scientific notation, however many digits are in the number right here, those digits will be significant. So this will be 4. And this one, there's a dot, so we start at the right. 1, 2, 3, 4, 5, 6 significant digits. There we are. Okay, so SigFigs have some special rules when we do math. When we add and subtract SigFigs, the answer will have the same number of decimal places as the value with the fewest decimal places. So let's just look at these examples. 613.5 plus 382 equals 995.5. Now, we have one decimal place in our answer, but because 382 does not have any decimal places, we can't have any decimal places in our answer to have the correct number of SigFigs. So our answer, we'll just round, will be 996. And on this one, we have 52.456 minus 0.1694. And that equals 52.2866. Now our answer has 4 places past the decimal point, but because 52.456 only has 3, we can only have 3 places past the decimal point in our answer. So then we will round that to be 52.287. There we are. When you multiply and divide SigFigs, the decimal places don't matter. What matters is the number of SigFigs total. And you want to have this same number of SigFigs in the answer as the value with the fewest number of SigFigs. So if you multiply 85 times 34, you get 2,890. Now that is 4 digits, but both of these numbers only have 2. So we can only have 2 digits in our answer. So we're going to round that, so that is 2,900, and that'll be it. And then with this one, we will divide 25.34 by 1.55 times 10 to the negative 4. So that equals 163,483.871. And it's helpful to move this into scientific notation because we know here from this one that we can only have 3 SigFigs in our answer. So if we convert that to scientific notation and round so that we have 3 SigFigs, it will be 1.63 times 10 to the 5th. And there are our answers. And here, remember to put the units on. And I forgot to write the units here, but that should be centimeters. So remember to do that. Okay. Now, dimensional analysis is a really awesome way that we can convert values from one unit to another. And we use things called conversion factors. So a conversion factor is like 12 inches equal 1 foot, or 1 gram equals 100 milligrams. And I think it will be easiest just to do some problems to show how this works. And here are some examples. So the first one is that the diameter of a red blood cell is about 3 times 10 to the negative 4th inches. And we want to know the diameter in centimeters. So we are going to use some conversion factors to help us figure this out. All right. Okay, so here's our diameter in inches, and we want to find it in centimeters. So 1 inch equals 2.54 centimeters, and that's our conversion factor. So you're going to do, you can draw a line. This is how I like to do it. And you always want the units to cancel out diagonally. So 1 inch will go down here because those will cancel out. And 2 okay. Hopefully you can hear me. I just had my audio disconnect for a second. Okay, so 1 inch equals 2.54 centimeters. And then we wanted to convert it to centimeters, so we'll stop there. And how this works is you're going to multiply across and divide down. So we're going to start here, and we're going to go across, and we're going to multiply. So 3 times 10 to the negative 4th times 2.54. And then we're going to divide it by 1. And this comes to be 7.62 times 10 to the negative 4th centimeters. And your units left will be whatever doesn't get canceled out. So there's that example. Let's do the other one. Okay. So we have some gold that is 1,228.40 per 1 ounce. And we know that 1 ounce from the information in the problem equals 28.35 grams. We also are told that 1 gold bar has a mass of 12.4 kilograms. What we want to figure out is how much one of these gold bars would cost. So we're going to start with this 12.4 kilograms up here at the top. Draw a line. Okay. First, we need to convert it into grams, and then we'll convert it into ounces, and from ounces into dollars. So 1 kilogram, we're going to put the kilogram on the bottom so these can cancel out, equals 1,000 grams. And we know that from this conversion factor down here, that 28.35 grams equals 1 ounce. So we'll put ounce here. So now the kilograms will be canceling, the grams will be canceling. And now we also know that 1 ounce, put it down here so these can cancel, equals $1,228.40. Okay, so let's figure out what this equals. We'll start by multiplying across and then go down and then across, go down. So the pattern will look like this. Multiply, divide, multiply, divide, multiply, until you get to your answer. So 12.4 times 1,000 divided by 28.35 times 1,228.4 equals let me write this down. And that is how much money one of those bars of gold would cost. So dimensional analysis is a great way to figure out how to convert things from one unit to another. Hopefully this video is helpful, and have a great day.